Tell me. Look into the notes. Where have you written last? What have you written last?
Ma'am, we have written time period.
We've done till time period. Okay, wait. Okay, see, till here have you time period? Okay.
Yes, ma'am.
Till here have you completed?
Yes, ma'am.
Okay. So this much part of it is done. Kinetic energy and all you didn't write? Just see.
No, ma'am.
Okay, just complete this part, this much, and this, and then I'll discuss the next portion. Okay. Now see what we will do, because this was in a continuous manner, so that's why I asked you to copy it till here. Notes you already have. Means the theoretical portion is already there with you. Right? I hope you received a PDF of the notes. Yes or no?
No, ma'am.
You have not received the chapter's notes?
No, ma'am.
Both of you, Lubna, you too.
No, ma'am. I also didn't receive.
Okay. I shared the notes long time back. Okay, no problem. What you can do is see for the theoretical part, because if exam is on 26th and it's already the 10th, and we have to complete this chapter, the next EMI is also there, and AC is also there. So the fifth chapter we can do later. EMI at least and AC, these two chapters should be done. So let's not waste the time in writing in the class. Either I'll share the notes again, I'll just tell them to share the notes with you again. And what you do, whatever theoretical part is done in the class, you take the screenshots of that. Numericals, you write it properly. Okay, so I'll just let me just discuss this chapter so that and we can complete it today itself. The question says a proton, a neutron, and an alpha particle enter in a uniform magnetic field. Calculate the ratio of their radii if they have the same velocity, same kinetic energy, same momentum, same potential energy. See how to deal with these kinds of questions. So when it says same velocity, first tell me what's the formula of the radius?
MV by QB.
mv by qb. So radius is equal to mv by qb. Now a proton is there, a neutron is there, and an alpha particle are there. So all these three enter a uniform magnetic field like this. Now magnetic field is present, B is already existing. The question says that you have to calculate the ratio of the radii if they have all these things as same. So R is equal to mv by qb is the formula. Now see, ratio of radii, basically you need to understand few things. Proton is there, neutron, and alpha particles. Charge is present and mass. There's a relationship between their charges and mass. So mass of the charge of the proton is E. Charge on the neutron is, see, when we talk about the charges and the masses, the ratios have to be taken. Okay, so the charge on the neutron is also E, while the charge on the alpha particle is 2E. And mass of the proton is mp. Mass of neutron is twice of the mass of proton, while the alpha particle's mass is 4 times the mass of proton. Why did we make everything in terms of proton? So that a standard is obtained and it is easy for you to take the ratio. In ratios, if you have two different quantities, it is difficult for you to obtain that. So what you do, you take the quantities that are same. Now R is equal to mv by qb. mv by qb. Now see, mass of all of these will be different. Velocity, it is saying, the question said that it is moving with the same velocity. So you will make the velocity also same. Magnetic field will already be the same because it is moving in the same magnetic field. So velocity is same, magnetic field is same. Basically, we can say radius is directly proportional to mass by the charge. So what you do for mass by charge? Ratio radius of the proton is to radius of neutron is to radius of the alpha particle is equal to mass by charge. mp by E is to 2 mp by E is to 4 mp by 2E. Now see, mp will be cancelled, E will be cancelled. This becomes 2. The ratio is 1 is to, from here 2 is to, from here 4 by 2, that is 2. This is the ratio. Have you understood this one?
Yes,
Okay.
ma'am.
Yeah,
Why have we taken for alpha 2 electron?
that's the charge on alpha particle. Alpha particle, no, there are charges present. So experimentally, this data has been extracted that the charge on the alpha particle is actually double, and the mass is 4 times the mass of the proton. All these are the experimental data. Okay, for neutron, it is same. The charge is the same, but mass is doubled. Okay.
So, ma'am, this will be given or we have to remember this?
Yes, you have to remember. Okay, it's better to be on the safest side and remember this. All right. Remember
Okay,
for
ma'am.
proton, neutron, alpha particle, these things only revolve. Second says same momentum. Now look, question says same momentum. For the same momentum, okay, by the way, what's the formula for momentum? Formula for momentum. Momentum, mass into velocity. So here R is equal to mv by qb. This whole term mv can be written as momentum. Okay. R is equal to q by v. Okay. So what we'll do? Charge, see, charges, the different charges are different here. Magnetic field will still be the same because all of the three are released in the same magnetic field. So we can say here, this is the same, this is the same. So basically, radius is inversely proportional to the charge. That's it. Are you getting? R is equal to mv by qb. Mv can be extracted as the momentum. So radius is basically inversely proportional to the charge that is present. So what we can say, the ratio of the radius of the proton is to deuteron is to the alpha particle will be just the reciprocal of the charges. Now proton is 1 by E, deuteron is 1 by E, while electron is the alpha particle is 1 by 2E. So E will be cancelled. Now see, this is coming in the denominator. If I multiply this with 2, this with 2, means all of these, if I multiply them with 2, what will happen? At least the denominator will vanish. So this will be 2 is to 2 is to 1. Okay. And momentum, this is 2 is to 2 is to 1. Are you getting it? Why did we multiply with 2? Is it because this was half? You can, if you want, you can write the answer as this also. 1 is to 1 is to 0.5. That is also correct. But I think it's better if we write it in the proper whole numbers. Got it?
Yes,
Okay. Third part says same kinetic energy and same potential is there. Same kinetic energy, look. If we have the same kinetic energy, see radius is, or one thing we can do for kinetic energy, you have written the formula of kinetic energy. Remember, right now you have written in the last class we discussed it. Q square, B square, R square by M. Something like this was the formula. Is it? Or 2M, sorry.
yes, ma'am.
Right? So we can say radius from here is basically 2 into mass into kinetic energy by, see, this will be under root, okay, and this will be 2m. This is qb. Getting it?
Yes, ma'am.
Okay, so r is equal to under root 2mke by qb. Now look, the question says kinetic energy is the same. Kinetic energy is the same. Magnetic field is also the same. Now root 2 will be common in all of it. So root 2 will also be cancelled. So eventually we can say radius is directly proportional to the root of the mass by the magnetic field. Okay, so this will be directly proportional to the root of the mass, sorry, not the magnetic field, to the charge. So R proton is to deuteron is to the alpha particle. This will be root mp. Look, this will be root mp by E is 2. This will be root 2 mp by E. to root 4 MP by 2e, as it is the values we have taken. That's why I say remember these values. It's better, because of what if it's not mentioned in the exam? The differences are not mentioned, and these things are somewhat mentioned in your NCRT, so you should remember it. Now root MP, MP, root MP will be cancelled. What are we left with? This is 1 is 2. This is root 2 is 2. Root 4 is 2. 2 by 2 is 1. So this will be 1. Same kinetic energy 1 is clear?
Yes, ma'am.
Okay. Coming to the last one. Same potential difference. This is the same potential difference. Same potential difference. See, this is completely different for you. You have not heard it. And this we'll be studying in the chapter Dual Nature of Matter and Radiation. Basically, what happens is potential energy is connected with the kinetic energy. There's a relationship that kinetic energy is equal to charge into the potential. Okay, kinetic energy is charge multiplied to the potential. So in the formula, R is equal to 2mke. We can write QV under root same thing divided by this will be QB. Correct. This was QB only. Huh? So what can we say? Now let's do one thing, class. Charge is coming above also, charge is coming below also. Let's multiply and divide it by root Q to rationalize it. Okay, multiply and divide it by root Q. Now root Q into root Q is Q. Q will be cancelled. So what do we get? We get this is equal to 2mv by QB. What is this? Root Q into root Q is Q, right? Root Q into root Q is Q. So this 2mv is left. This is already in the denominator. This is in the denominator. This in the denominator. Right? Now see, what is it proportional to? You can clearly see the radius is directly proportional to mass by the charge. But how is it different from other parts? Because a root is present. In the other parts, root m by q wasn't there. Root m by only q. This is also proportional to the reciprocal of the charge. Okay, this is proportional to this one, the first one, directly m by q. Nowhere we had root m by q, so that's what the difference is. Now let's take the ratio. Rp is to Rd is to R alpha will be root of mass of proton by E is to root of mass 2 mass of proton by E is to root of 4 mass of proton by 2E. See, root E will be cancelled, MP, root MP will be cancelled. This will be 1 is 2. This is root 2 is 2. This will be cancelled and it will give you 2, which is again root 2. Clear? Kutsi and Lupna, both of you?
Yes, ma'am. Yes, ma'am.
Okay. Please write this numerical. We'll come to the fourth case, the last case. And that's a theoretical part. Just write down from here. Numericals, at least write it properly. The theory part, you can leave space and complete it later so that we are able to complete a lot of syllabus. Please write. See, uh, fourth case is basically when the particle is acting at any angle. So what happens here is, let's say a charged particle is there, Q. Okay. This is moving with a certain velocity in some magnetic field, V. Now, some angle, let's say theta is made with here with the magnetic field. So, the charged particle, what we'll do, we'll resolve the velocity first. Because see, this is neither along x-axis nor along y-axis. So, what we'll do, we'll resolve it first. So, this becomes v cos theta. The perpendicular becomes v sine theta. Okay. Now see v cos theta, this one, and this is v sine theta. So v cos theta is the parallel component, while the perpendicular component is v sine theta. So moves the v parallel component moves the charge in a straight line. Okay, and the perpendicular moves the charge particle in a circle. So, see, path will be helical. Eventually, what happens? The final path that occurs, like if this is not making an angle of 90 degree, this is not making an angle of 180 degree or 0 degree, this will be, the path will be helical. Why? Reason is that the parallel component, now which you see, this will provide a straight line, and the perpendicular component will provide a circular path. Then again a straight line, then again a circular path, then again a straight line, again a circular path. Like this will occur. Okay. Uh, Path will be helical. This is the fourth case. Now coming to the Lorentz force. That screenshot you can take. I'll give you time. Just listen to me first for the Lorentz force. Lorentz force is basically, what if the charged particle is, magnetic Lorentz force is that if the charged particle is present in the electric field as well as in the magnetic field. Means magnetic field and electric field, both the fields are present. You have the electric field, you have the magnetic field. Okay, if it electric field and the magnetic field. So charge, the electric field and magnetic force both are existing in this case. So what will be the, what eventually will be the net force which is acting? We can say for the net force, we can say it is the electric force plus the magnetic force. Electric force is Q into E plus the magnetic force is Q V cross B. F net is equal to charge, electric field plus V cross P. Okay, so this is the net force. Charge is E plus V cross P. Now coming to the direction. Direction of the electric force would be charge. If the charge particle is positive, it will move in the same direction as that of the electric field. Okay, and if the charge particle is negative, it will move in the opposite direction as that of electric field. And for the magnetic force, we have the right hand thumb rule that we've already studied. Okay, we'll see this question. Now you take the screenshot till here, and let's practice this numerical. First, let us practice, then you can take the screenshot. This says a particle of 2 coulomb is moving with velocity of I cap minus 2 j cap, and electric field is, magnetic field is. It says calculate the net force. So if we have V cross B, let us calculate this first. V is I cap minus 2 j cap. So how do we solve the cross product? See, velocity is given as I cap minus 2 j cap. Magnetic field will be I cap minus j cap minus 5 k cap. Okay. Now, if we have I cap, j cap, k cap. Now we have velocity first. Okay, velocity, this is 1. J cap's coefficient is minus 2. There is no k cap. It is 0. Magnetic field, here this is 1. J cap is minus 1. K cap is minus 5. Now let's take the cross product. First we solve I cap. What we do, we cut the column and the row of it. And then we multiply. This is from your class 11, the basic cross product. I'm just revising it. So minus 2 into minus 5 you will write. Minus 2 into minus 5 minus 1 into 0. Okay. This much is I cap. That is the first part. What you just multiply diagonally down minus diagonally up like this, you write. Then for j cap, what we do? For j cap, there is an exception that we write minus. We don't add. Okay. And we cut the j caps column and j caps row. I hope you all have done all these things in class 11. Now 1 multiplied to minus 5 minus 1 multiplied to 0. K cap row we'll now cancel. Now for K cap you can put a simple plus. Now 1 into minus 1 minus this will be 1 into minus 2. This is K cap. Okay. So this can be written as minus 2, minus 5, minus 10. This is 0. So no, plus 10 actually. 10 I cap. This is minus 5 minus, this is minus 5 here. This is 0. Minus minus 5 will become plus 5. Okay, this will be plus 5 j cap. This is minus 1 here. This is minus 2. So minus minus will become plus. So 2 minus, see, this is minus 2. Minus 2 minus is plus 1, plus 2. 2 minus 1 is 1. Again, so plus K cap. This is V cap, V cross V. Okay, all right. So this is the V cross V, and electric field will be, electric field is 2 I cap minus 3 J cap. 2 I cap minus 3 J cap. So what do we have next? We add this with the V cross V. Okay, electric fields component you added with the V cross V. So this is electric field is 2 I cap minus 3 J cap plus this is 10 I cap plus 5 J cap plus K cap. Okay, so this will be 12 I cap. This is J cap. This is K cap. Okay. Finally, the net forces charge multiplied to E plus V cross B. Okay, so that is 2 into 12 I cap plus 2 J cap plus K cap. So this is equal to 24 I cap plus 4 J cap plus 2 K cap. Finally, this much of Newton will be the answer. Got it? How have we done this? First is you take the cross product. I'm just marking it. You first take the cross product, that is V cross B. Okay. Then you added E plus V cross B. And then force this, finally this will be Q into E plus V cross. Okay, Kutsi and Lubna.
Yes, ma'am.
Any
Yes,
doubt?
ma'am.
Clear?
Yes, ma'am.
Okay. This is also there. This I'll discuss later. Do one thing. Till here, take the screenshots, leave the space, and then copy down this question in detail. Don't waste your time in writing this part, as we have already discussed. From here, you can start taking the screenshot. Let me shut the camera. Wait. Just text are done in the chat box so I can scroll. Okay, see, done till here. Lubna, you too?
Yes, ma'am.
Okay. Now there is one more force on the current carrying conductor that we calculate. See, if a wire is present where electrons are moving with a certain length. Okay. Now, length of the conductor is there as L. A is the area of the cross section, I is the direction of the current, N is the number density of the electron. Volume of the wire is area into the length. Length of the wire is there, area of the cross section is there. Now, total number of electrons, let's say, is Na into L. Okay, NaL. Now, see, if we have the total number of electrons as NaL and we calculate the quantization of charge, okay, using the quantization of charge, Q is equal to Ne if we use. So, total number of electrons that we will be having will be NaL, basically the number of electrons multiplied to the electronic charge, E. This will be, so total charge will be NaL into E. Okay, this is the electronic total charge that is present. Now, when I talk about the force here is charge multiplied to velocity into magnetic field. That's what we studied. So, charge is NaLe. The magnetic force is there. Okay, and the let me write down, instead of the magnetic force, let me write down the velocity is present. Now, velocity of the electrons are known as the drift velocity. Find multiplied to the magnetic field. Now, class, if you remember, there was a formula. I think we haven't discussed. No, you must have studied. I is equal to NEA VD. This is the drift velocity. NEA VD. This is the current. F is equal to, this is I. This is L cross P. This is the magnetic force. So magnetic force is ILB sine theta, magnetic force acting on the wire. So this is the formula of it. Okay, L cross B means LB sine theta. Okay, IL cross B, ILB sine theta. Now see, this is a current carrying wire. 5 amperes of current is there, 10 meter is the length, magnetic field is B. Now if I calculate F is equal to BIL sine theta. Okay, B is the magnetic field, that is 2. I is 5 ampere, length is 10, and this will be sine 90 degree. So this is 10 into 10, that is 100 Newton. Okay, now let's look at the direction. How to see its direction? Take the right hand, put it in the along the direction of current. Okay, so when we put it along the direction of current, this is let's say 5 ampere, this is towards the right, so we'll put our palm towards the right. Now magnetic field is present inside. Okay, this right hand, current towards the right, the magnetic field, curling the fingers towards the magnetic field. Where is the thumb pointing? Thumb is pointing upwards. So this is this much of taken. Similarly, one more question. F is equal to BIL sine theta. Magnetic field is 2, current is 5, length is 10. This is sine 90 degree. So this is equal to 100. Again, 100 Newton is there. Now look at the direction. Current is upwards. So we'll still take our palm to be upwards. Now magnetic field lines are coming outwards. So outwards will be like this. When we curl it, thumb is pointing towards the right. So this is I cap. This is how we write the complete answer. That completes with the Lorentz force also. I'll start with the force between two parallel wires. Take a screenshot still here and note down these two numerics. Am I clear till here? Both of you, Kutsi and Lubna?
Yes,
Okay, please take the screenshots. See, when we talk about force between two parallel wires, basically it's like two parallel wires are present. One is exerting the force on another. So what we do, we take the magnetic field of the first wire. So as we discussed, magnetic field of infinitely long wires are mu naught I by 2 pi a. So mu naught here, this is I1 by 2 pi t. Now the force on the second due to the first will be I2 L B1 sine theta. See, you are taking the force on the second wire due to first. Because it is due to the first, you are taking the magnetic field of the first. So I2 L B1. Okay, so F21 will be equal to I2L mu naught I by 2 pi t. So F21 is equal to mu naught I1 I2 L by 2 pi t. This becomes the force. Okay. And see, if I bring this L here in the denominator, that will be force per unit length, force divided by length. So that will be mu naught I1 I2 by 2 pi d. Okay, and similarly, when you calculate F12, that will be mu naught I1 I2 2 pi d same, because eventually this is getting, the length is getting divided. So this is the formula that you need to remember. This you have to remember if length is mentioned, if length is not mentioned. You take the force per unit length and you solve this. Okay. When the current is moving in the same direction, whether upwards or downwards in both the wires, it's in the same direction. Okay, both are upwards or both are downwards. Then the conductors attract each other. Okay. And if they are in the opposite direction, one here, one above, one downward, then we take this as opposite. Now, sometimes the question comes to define 1 ampere in terms of this wire. So, how will you define it? Look, F21, this is mu naught I1 I2 by 2 pi d. So, if I said 1 ampere, if I have to divide, I'll put the value of current as unit amperes. Okay, we'll put this as unit amperes. F21 will be mu naught I1 I2 by 2 pi t. So D, if we take D as 1 meter, current as 1 ampere, I1 as 1 ampere, I2 as 1 ampere, and we put these values, we get this mu naught by 2 pi. If I put mu naught as 4 pi into 10 to the power 7, I will eventually get this as 2 into 10 to the power minus 7 Newton. Okay, if I write this 2 into 10 to the power minus 7 Newton. So 1 ampere is the current when flowing through two long conductors separated by 1 meter gives 2 into 10 to the power minus 7 Newton of force and can attract or repel each other. So this is the value. Let's see a question. These are two wires that are present. So it says for force per unit length. So simply we'll use the formula mu naught I1 I2 by 2 pi d. Okay, current first is 2 ampere, second current is 10 ampere, separation is 2 meter. So F21 will come out to be the same, F12 will also be the same. It's just that direction will be different. Because see, current is flowing in the same direction in both the wires, right? Both the current is flowing in the same direction in both the wires. So they'll attract each other. So one will go towards the right, two will go towards the left. Okay, is this topic clear?
Yes, ma'am.
Okay. Take the
Yes, ma'am.
screenshots of this and then note down that question. Then I'll discuss magnetic dipole moment, one part. Okay, just write this. Done. Is it done?
Yes, ma'am. Yes, ma'am.
Okay. See, when we talk about a magnetic dipole, so magnetic dipole, when we talk about, so formula of magnetic moment is area multiplied to the current. Now, what we do for this formula, remember this because we'll be using in the formula of the torque. Okay, magnetic moment is current into area, and this is equal to, and if you have single turn present in the coil, it is current into area. For n number of turns, it is number of turns multiplied to current into area, that is nia. Okay, uh, just a second. Okay, so see, you have to write the direction of the magnetic dipole, whether which polarity is existing, south polarity is there or north polarity is there. You write just an S for the south polarity. Okay, put these arrows, and then whatever arrows are made, you make it on the circular ring as well. Okay, so that is clockwise. Similarly, when you put north polarity in, these arrows will show anti-clockwise. So this is a way just to remember it. Otherwise, south polarity for clockwise, north polarity for anti-clockwise. Main is important is magnetic moments formula. Current into area. Okay, magnetic dipole moment. Uh, Okay, direction I didn't tell you. Direction is, see, along the sense of current, just curl your fingers, thumb will give. Whatever is the direction of magnetic field for a circle, same. Like, look at this question. This is a circle with radius 1 meter, number of 10, a number of turns 100, current is 2 ampere. Okay, magnetic moment is NAI. Number of turns is 100, I is 2, area is pi r square, that is pi into 1 square, which is equal to 200 pi ampere meter square. Okay, now see, we curl the fingers as the current is moving, thumb is pointing inward. So this is minus k cap. Okay, and see this one. So here we have a square. So the side is 2 meters. Okay. Now area of the square will be 2 into 2. Current is 2 ampere. Number of turns is 100. So that becomes 800. Now how the current is flowing? The current is flowing anti-clockwise like this. So curl the fingers anti-clockwise, thumb points outwards. That is K cap. Okay, so this is how we write the magnetic moment. All right, so this is a small topic which you should know. Just take the screenshot till here and just note down the questions. Am I clear? The magnetic moment is clear? Magnetic dipole moment.
Yes, ma'am.
Anything, Kotsia, Lubna, you want to ask from this chapter, both of you? Anyone?
No, ma'am.
Okay. Please take the screenshots of this one. Okay, see, coming to the topic torque. When we have a coil, let's see the direction of the forces. See, in the coil, this I think we discussed earlier also that take the direction of the current along the palm. Okay, and then curl the fingers along the magnetic field. Now, magnetic field is this. This coil is coming outwards. Magnetic field is towards the right side. Look, this part. The coil is present like this. This is the coil. Current is coming towards me like this. So I'll take my hand like this. Current is coming towards me. So I'll take my hand like this. Curl the fingers towards the magnetic field. Where is the thumb pointing? Upwards. So that's why this force is upwards. Okay. This is the front part. Now the current is moving downwards. So I'll also take the current downwards. Magnetic field is towards the right, thumb points outwards. Okay. Here the current is flowing inwards. So I'll take the current inwards. Magnetic field is towards the right. So I'll have to curl it like this. Thumb is inwards, downwards. That's why this is downwards. Current is flowing upwards. We'll also take our palm upwards. Magnetic field is towards the right. So if I curl it, this points inwards like this. Is it clear why all the directions are in the opposite side? Is it clear?
Can you explain again the figure?
Okay. See, there is basically a coil that is put. Okay, like this. This is a coil that is put, and current is flowing like this. Like this, it is going then out in like this. The current is flowing. Okay, so what is happening when the current is coming to us? We are seeing the direction of the forces. This is the coil. These purple lines, these are the magnetic field lines. This is how the current is flowing. Okay, and the plane of the coil makes angle theta with the magnetic field. Length is L and the breadth is B. So when we talk about the forces, current is coming inwards. Okay, the current is coming inwards. So we take our palm along the direction of current. And where is the magnetic field? Magnetic field is towards the right side. So we curl the fingers towards the right side. Where is the thumb pointing? Upwards. So that's how we get this force. Likewise, the other forces. This is put in this manner, in the YZ plane. Okay, now clear?
Yes, ma'am.
Okay. So here what will happen? All of these forces will cancel each other eventually and we'll get a translational equilibrium. But when we talk about the torque, torque will exist. And the formula of torque is basically torque is M cross B. Okay, where M is the magnetic moment, B is the magnetic field. This M is the magnetic moment and B is the magnetic field. When you put the formula of magnetic moment AIB, NAIB, so total will become, the torque will become NAIB sine theta. Sine 90 is equal to 1, theta is 90, you get the maximum value of the torque. Okay, so this will be used in moving coil galvanometer. Just a small topic is there. On Sunday, just tell me one thing, class. Do you want to start with EMI directly or do you want to do chapter 5th? Which chapter do you want to do next after this? Just tell me the chapter because this is almost over.
Chapter 5.
Chapter 5th? Okay.
Yes, ma'am.
Okay. Just take the screenshots of this.
Ma'am,
Yes. Yeah, Lubna.
from Sunday, our school is from the normal timing, like morning. So again, we need to change the class timings.
Okay. Your timings are shifted.
Yes, ma'am.
Now, what's the time? So, will it be again shifted? Like, does it keep on changing in your school?
No, ma'am.
Okay. Let's see then for Sunday morning, then you'll not be able to take the class, no? You'll have your school.
Ma'am, we will be free in evening. Our school will be in morning from Sunday onwards.
Okay. All right. So in the evening you'll be there. Let's see. Okay, we'll inform you about the timings. Okay.
Okay,
I'll
ma'am.
just
Thank you.
talk to the team. Okay. Just take the screenshots of these. Okay, if it is done, so I'll stop here. In the next class, we will just contact you for the class because Sunday evening I already have classes. So it might not be on Sunday. Let's see whenever we can have the class. I'll just inform both of you. Okay.
Okay,
And
ma'am.
chapter
Thank you.
fifth is the chapter that you both want to start. The next one, just the next chapter, no?
Yes, ma'am.
Yes,
O-
ma'am.
Okay, all right. Then I'll start with that. Okay. Okay, then thank you. Okay, Lafis.
Thank you, ma'am. Yeah.
Thank you, ma'am.